some complex problems that can be solved on current computers only in years will be able to be solved in seconds on quantum computer. So today is the time to learn quantum computing. In these modules, we will start from basics and cover advanced topics in quantum information systems. So now we give some examples of problems which can be solved on the quantum computers in exponentially less time than the classical computers. One of the most important example is prime factorization of large numbers. This is an important classical problem which takes exponential amount of time on classical computers. And this effect is used in the main cryptography algorithms like RSA and so on today. In quantum computers, a new algorithm has been invented, that is Shor's algorithm, which can solve this problem in polynomial time. And this has resulted in a very large confusion in today's world, because now all cryptography algorithms currently used can be very quickly solved. Then, in fact, this has resulted in what is called post-quantum cryptography also. Another important problem is solving systems of linear equations. These equations are being used everywhere, and these have very important applications. There is a quantum algorithm, HHL, which can again give exponential speed up for these problems. And that algorithm can also compute matrix inverses. Another very important example is Fourier transforms. FFTs in classical computers are the basis of today's modern signal processing algorithms. There is a corresponding quantum Fourier transform, which again gives exponential speed up over FFTs. And same algorithm can be used to find the eigenvalues of many operators. These very important speed ups that you obtain in quantum computers have resulted in immense activity in quantum machine learning. Machine learning, as we know, is very important today. AI and machine learning are the buzzword being used everywhere. If you use quantum computers, we can speed up the algorithms in these important applications as well. In addition to those above important examples where quantum computers can provide exponential speed up, there are examples where it may not provide exponential speed up, but it provides polynomial speed up. And a very important example there is search algorithms, search problems for unstructured setup. There is a quantum algorithm called Grover's algorithm. This provides quadratic speed up over any classical algorithm in this very important problem. And this can then be used also for combinatorial optimization problems. In addition to these, quantum computers and quantum information processing is being used in many other important applications as well. For example, in quantum communication, there is quantum key distribution. We mentioned earlier that Shor's algorithm threatens today's cryptography algorithms like RSA, but quantum information process also helps us in the same problem for distribution of private keys to do cryptography. This is called quantum key distribution. This, as using this, we can between two users provide a private key on a public channel. So this helps in cryptography via the quantum information processing. Today also, most of the communication happening in the world is either via wireless communication, which is the last mile communication, but rest of the communication is via fiber optic communication. Mostly at the moment, fiber optic channels are being modeled in the classical way. But if you model them via quantum information processing into quantum channels, that can increase the channel capacity of these channels, and this provides immense gain in our everyday communications. Another important current application is quantum sensing and quantum radars. And using quantum radars, we can get far more detection ability than is possible via the classical radars. So this is another very important strategic application today. How we are able to achieve via quantum computing such immense gains over classical computers. The main reasons are in quantum domain, the systems can be in superposed states. This provides unprecedented parallelism for the quantum systems, which is not possible in the classical case. In the classical case, to gain n times parallelism, you have to have at least n parallel hardware structures. But in quantum computers, with one hardware, you can have indefinite amount of parallelism. And this is a very, very important gain that you obtain in quantum computers versus the classical computers. Another very important unique thing in quantum system is entanglement. It is a very important resource, powerful resource for computation and communication, and entanglement is not possible in classical computers. There's one more difference between classical computers and quantum computers is that in quantum computation, all computations are reversible, while in classical, they don't necessarily have to do that. After explaining all these important gains that you can obtain from quantum computers as compared to classical computers, let us also mention that there are some limitations as well. One important thing is for us to understand any function computable on a classical computer is computable on a quantum computer. That, of course, is the advantage of quantum computer. But the converse is also true. That means quantum computers will not compute any function which is not computable on classical computers. And there are functions which are not computable on classical computers. Another important limitation is that so far we have not found any example where quantum computers have been able to solve an NP complete problem in polynomial time. Although we have given many examples of exponential speed up, but we have not been able to get such speed up for NP complete problems. However, we have given many examples where, because of which quantum computers are going to be very, very beneficial for us in everyday life. In these modules, we will have three modules. In one, quantum computing one, we will provide the introduction of what it is. We will also explain quantum axioms, which differentiate quantum computers from classical computers. Then we will explain quantum gates, which are the uh, corresponding things of as in classical gates and so on. We will explain quantum circuits, which correspond to the digital circuits, and then we will explain the basic quantum algorithms, the ones that we have mentioned here in this introduction. After this, there will be four quantum modules in quantum 1. In quantum computing 2, we will explain quantum machine learning. The basic algorithms that we have provided in quantum computing 1 will be used for machine learning applications. We will give another model of quantum computing that is called adiabatic computing, which provides different advantages compared to the gated systems that we are explaining in quantum computing 1. In quantum computing 3, we will discuss about quantum communication and function theory, QKD, cryptography, basics of quantum ECC, error correction course, state detection, and quantum information theory. So please subscribe with Google email ID to reach these modules. Thank you very much.